With the combined gas law, we are now going to be looking at more than two variables. In this case, notice the factors that can vary. Pressure can vary, volume can vary, and temperature can vary. We're assuming that our amount of gas particles is going to remain constant. Now you might have guessed by the name of the law, but our combined gas law is going to take the three laws we've learned up till now, Boyle's, Charles, and Gay-Lussac's, and combine them into one formula. The formula looks like this. P1 times V1 divided by T1 equals P2 times V2 divided by T2. Notice all the 1's are on the same side and all the 2's are on the same side, indicating that one side is for the original and the other side is for after the change. Now there's another way that this equation can be written. It can also be written P1 times V1 times T2 equals P2 times V2 times T1. The reason it can be written like this is assuming we've already done the cross multiplying. For instance, P1 times V1 times T2 would be equal to P2 times V2 times T1. Some students like this way right here because it keeps all the 1's on the same side and all the 2's on the same side. Some students, however, prefer this equation because it already does the cross multiplying for them. Whichever equation works best for you, you'll get the same answer. Finally, notice the units that each of our variables have to be in. Pressure and volume can still be in any unit so long as they are the same on both sides, whereas temperature still needs to be in Kelvin. Now that we know the law, let's look at an example. If a balloon has a volume of 3.2 liters, a pressure of 720 torr, and a temperature of 34 degrees Celsius at sea level, what volume will it occupy if it raises in the air where the temperature is 23 degrees Celsius and the pressure is 680 torr? That's a lot of information, a lot of variables, and a lot of numbers. Let's go ahead and start breaking that down so we can try to make sense of this situation. Sometimes it helps to draw pictures to indicate what is happening in the problem. At sea level, you apparently have a balloon that has a volume of 3.2 liters, a pressure of 720 torr, and at a temperature that is 34 degrees Celsius. Then what happens is the balloon raises in the air. As the balloon raises in the air, the conditions change. The question is asking what volume would the balloon be at there if the new temperature is 23 degrees Celsius and the pressure changes to 680 torr. By doing this, we have now not only analyzed the problem, but we've given a good visual of what's actually happening. We're solving for a volume given the original conditions. Before we can actually use our combined gas law, which is P1 V1 over T1 equals P2 V2 over T2, we need to make sure all of our units are in the proper units in order to use this equation. My pressure is in torr. Since this is the same on both sides, we can continue and keep it like that. My volume is what I'm solving for, so I know that since it's liters here, my volume solve will be liters on the top. The only thing that needs to be converted are the temperatures. Both of my temperatures are in Celsius, and that can't be true. It has to be in Kelvin. So let's look at my original temperature. 34 degrees Celsius is the same thing as 307 degrees Kelvin. 23 degrees Celsius is the same thing as 296 Kelvin. Now that I've got my units converted, now I can plug in the information. My P1, which is down here, is 720. The volume at that point was 3.2 liters, and the temperature was 307 Kelvin. Now let's go up here to where the conditions changed. The pressure has now changed to 680 torr. My volume is what I'm solving for, and the new temperature is 296 Kelvin. Now let's cross multiply. 720 times 3.2 times 296 will equal 307 times 680 times V2. Rewriting that, it will look like this. Now that you have all of your information plugged in, the last thing is to solve. We do 720 times 3.2 times 296 to get our left side equaling 681,984, and that's equal to 680 times 307 times V2, which gives 208,760 V2. To get V2 by itself, we divide both sides by the 208,760. Those values cancel, and this side will give me my answer. By taking 681,984 divided by 208,760, my volume is solved for. I get approximately 3.2668, and so on. Let's just check our sig figs before we end. All the information given to me is given with a certain amount of sig figs. 3.2 is 2. 720 is 2. Remember that 0 does not count because there's no decimal in the number. 34 is 2. 23 is 2. And 680 is also 2. Since my lowest number of sig figs was 2, my answer would be 3.3 liters. This concludes the video lesson on Guy-Lussac's law and the combined gas law.